Assalamualaikum and greetings to all. So this is group 2 for material science assignment, and this group gonna do about copper aluminium alloy. So this is our group members consists of Aieman Haziq, me myself, Farhanah Husna, Hafizuddin Haziq, and Ashraf Adha. So some introduction about copper aluminium alloy. Copper aluminium metal is multifunctional and has great mechanical, electrical, thermal properties. And these copper aluminium alloys employ electrical cables, power transmission line, and electrical connections. It is because these alloys are strong and great conductors. It is also used in vehicle and aerospace heat exchanger, radiators, heat sink, and other cooling equipment due to their thermal conductivity and technical properties. So this is some overview about the phase diagram of copper aluminium alloy. So we have some explanation of phase diagram, which is about liquid phase, alpha phase, and theta phase. Liquid phase is about the alloy is completely in molten state. Alpha phase refers to a uniform mixture of copper and aluminum in solid state, and theta phase is during isothermal aging below the detector temperature. So what is isothermal reaction? This phenomenon of reaction relates to the precipitation of the theta phase, which takes place at temperatures lower than detector temperature, maybe 548 Celsius degree. And this process involves several of stages, which is we have homogenization, quenching, aging, and also diffusion and precipitation. So for intermediate reaction, it is relates to the formation of distinct compounds or phases that occur due to interaction between copper and aluminum present in alloy. So these intermediate compounds are known to exert significant effects on the characteristic and performance of alloy. And the crystal structure and the properties of this compound show distinct difference from those of the pure copper and aluminum phases. And the changes in composition can have an impact on the mechanical strength, hardness, electrical conductivity, and thermal stability of the alloy. So it's the factors that contribute to intermediate reaction. We have three factors here, which is presence of other alloying elements, temperature, and also time. So for solid solution, it is occurred through two different processes, which is solidification and homogenization treatment. Solidification is when the atoms arrange themselves into an ordered structure, forming a solid solution as the alloy cools. And for homogenization, in order to achieve a uniform distribution of alloy elements, it is subjected to a homogenization treatment. So this is my phase diagram that will be explained by me, Farhanah Binti, and my metric number is A21EM0176, and I'm going to explain about 33% cuprum, which occurred for eutectic, and 50% cuprum for hypoeutectic. So eutectic zone formation is started at the liquid phase at the molten state, temperature above the liquid temperature, and then the eutectic temperature will reach by the alloy as the temperature decrease around 548 degrees Celsius, and the eutectic zone formation will start from this temperature. And then the formation of alpha and theta will occur when the eutectic temperature reach, and the nucleation and growth of the alpha, theta phases will occur from the liquid phases. The solidification process results in a lamellar structure, and the process of eutectic transformation, the atoms will undergo redistribution and fusioning, resulting in the formation of alpha and theta phases, and then the eutectic transformation will reach its final stages when all the areas undergo solidification. For hypoeutectic, we know hypo means below. So hypoeutectic composition is an alloy with less copper than eutectic composition, and the solidification will begin when the molten alloy temperature decreases below the liquid temperature. And as temperature decreases further, the remaining liquid becomes an eutectic formation alpha and theta phases. And at the eutectic temperature, this eutectic reaction will happen, and the process of hypoeutectic formation will remain until the complete solidification of liquid phase, resulting in formation of composite structure, consists of primary alpha phase and eutectic alpha theta lamella. So this is the microstructure for eutectic and hypoeutectic. Those microstructures have lamellar structure because it is in eutectic phases. And this is the cooling curve. It may have some different for hypoeutectic, which is having primary alpha theta formation and primary alpha theta growth. So this is some explanation for the cooling curve. We have phase cooling, primary alpha theta formation, primary alpha theta growth, eutectic phase nucleation, eutectic phase growth, and eutectic phase complete. So for composition and amount of phases at one temperature, I choose at temperature 610 degrees Celsius, there would be two compositions occur, which is 3.5% cuprum and 40% cuprum. At 3.5% cuprum, it will be two phases occur, which is alpha phase and alpha plus theta phase. And for 40% cuprum, it will be also two phases, which is alpha plus liquid phases and alpha plus theta phases. I think that's all from me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. I'm Muhammad Hafizuddin. Today I will explain about the two different type of the aluminium copper, which are hypoeutatic and hypoeutatic. Where hypoeutatic for 20% copper and hypoeutatic 45% copper. So this is the phase diagram for aluminium copper alloy. There are four different temperature as we can see in the phase diagram, which shows the different transformation of the microstructure. Next, I will explain about the transformation during the solidification process of hypoeutatic in aluminium copper alloy. So firstly, the transformation of aluminium copper for hypoeutatic region undergoes the process of transformation from the liquid phase to the solid phase, which involves the changes of microstructures at different temperatures. The alloy is in the hypoeutatic region due to the less percentage of copper compared to the eutectic composition. Initially, the liquid alloy contains a higher percentage of aluminum compared to the eutectic composition, which forms the alpha of primary solid phase. And then the solidification process starts when the molten alloy temperature decreases below the liquid temperature. As the alloy cools, the primary solid phase, which contains copper, undergoes the solidify process first. After that, the alloy temperature continues to go down while the liquid composition shifts towards the eutectic composition. When the composition reaches the eutectic composition, where it lies at 548 degrees Celsius, the remaining liquid follow the eutectic reaction. Last but not least, as the temperature goes further down, the remaining liquid transforms to the alpha and theta phases. So the microstructure consists of primary alpha dendrites surrounded by a finely divided eutectic mixture of two solid phases, which are alpha and theta. The process of hypoeutatic transformation remains until the solidification process of liquid phases is completed. The final microstructure consists of primary alpha phase and eutectic alpha and theta lamellar structure, which are the theta phase in brown or black color, while the alpha phase in white color. Alright, next I will explain the transformation of hypoeutatic during the solidification process in aluminium copper alloy. The solidification process for the hypoeutatic region is slightly same as hypoeutatic region, which occurs from liquid to solid phase. But there is the difference between the hypoeutatic and hypoeutatic, where hypoeutatic have more percentage of copper compared to the hypoeutatic. The aluminium copper alloy is in the hypoeutatic region due to the composition of alloy, which has more percentage of copper than eutectic composition. Then the solidification starts when the molten alloy temperature decreases below liquid temperature. The liquid alloy contains a higher aluminum percentage than the eutectic composition that creates the primary theta of the primary solid phase. When the alloy cools, the primary solid phase that contains copper solidifies first. Then the temperature of the alloy keeps decreasing until it reaches the eutectic region at 548 degrees Celsius. The eutectic phase formed by the lamellar structure, which involves the structure of solid solution and the eutectic compound. The eutectic lamella develop depends on the alloy composition and cooling rate, fast or slow rate. The temperature of the alloy continues to go down, transforming the remaining liquid into the alpha and theta phase. The hypoeutatic transformation process continues until the remaining liquid phase fully solidifies and then produce the final microstructure, which is an eutectic lamella structure, which contains alpha in black or brown color and then theta in white color. Next, this is the microstructure of solidification process for hypoeutatic region. As we can see at the first temperature, the microstructure is in the liquid phase. After that, when the temperature decreasing, the primary alpha started to form in the remaining liquid. As the temperature goes further down, the lamellar structure and the grain boundary started to form between the primary alpha in the microstructure. After that, at the temperature 4, which is the room temperature, the size of the grain boundary increase, and then we can see the alpha phase and the location of theta phase, where the theta phase located at the grain boundary and the alpha phase is in the white color while the theta phase in the black color. After that, this is the microstructure of the process for hypoelectric. The flow is same as the hypoelectric but slightly different, which we can see the first temperature, the liquid phase is in the microstructure, and then when the temperature goes down, the primary theta start to form at the liquid, and then when the temperature goes further down, the lamellar structure and the grain boundary started to form between the primary theta. After that, we can see the size of the grain boundary for the microstructure increase, and then we can see the alpha located at the grain boundary, which is in black color while theta is in the white color. Next, I will explain about the cooling curve of the solidification process for hypoelectric and hypoelectric. We can see the cooling curve for the hypoelectric and hypoelectric is the same trend, but there is slightly difference in terms of temperature. For hypoelectric, the cooling phase started to decrease from 700 degrees Celsius to 630 degrees Celsius. And then the primary alpha formation started at the 630 degrees Celsius. The temperature slightly increased and then goes down until it reached the 548 degrees Celsius. Between the 630 and 548 degrees Celsius, the primary alpha grows at this region. And then the eutatic phase started at the 548 degrees Celsius and keep at the same temperature until the eutatic phase ends. And then the solidification process continues and until it finishes. After that, for the hypoelectric region, the cooling phase started to decrease from 700 degrees Celsius until 580 degrees Celsius. The primary theta formation started at the 580 degrees Celsius until 548 degrees Celsius. The primary theta formation, at the graph you can see the temperature slightly increased at the primary theta formation when it started, and then between the 580 and 548 degrees Celsius, there is the primary theta growth in this region. After that, it is same as hypoelectric. The eutatic phase start at 548 degrees Celsius, and the temperature keep at the remaining same the temperature, which is 548 degrees Celsius until the solidification process ends. Next, this is the composition and amount of phases at one temperature. As we can see in the phase diagram, this is where the composition at 400 degrees Celsius and 15 with percent copper, which is this region lies at the alpha and theta phases of the aluminium-copper alloy. Based on the temperature of the alloy, which is 400 degrees Celsius, and composition of the alloy at 15 with percent copper, we can see the alpha is 45% while the theta is 55%, where we can get this from the formula of the phases fraction, and then we can get the alpha and theta, how many percentage of them. Therefore, the majority composition of the alloy in this region is alpha and theta, which is the percentage of alpha and theta is 45% and 55% respectively, at 15 with percent copper, which lies at 400 degrees Celsius.
Hi and Assalamualaikum. My name is Aieman and my metric number is 821EM0013. Now I am going to continue and explain about my phase diagram with detail on transformation during solidification process. Also, I am going to show you the sketch of the microstructure and cooling curve for this percentage weightage, and last but not least, I am going to show the composition and amount of phases at one temperature that I already choose. So let's dive into my phase diagram of copper aluminium alloy. So the marking pen is my choosing percentage weightage in this phase diagram, and I choose one with hypoelectric reaction and the other one is hyperelectric reaction with 10% weightage percentage and 40% weightage percentage of copper. I also already labeled the state that I want to be precise in this video. So first, we will go through the hypoeutectic transformation and get to know what is happening when this alloy solidified. You can read this detail to understand what is going on, but I will explain to make it you understand better. So first, when the hypoeutectic copper alloy transformation, it indicates that change in this microstructure takes place when it solidifies from a liquid state to a solid state. The alloy is referred to as hypoeutectic when the concentration of a solute, in this case aluminium, is lower than the eutectic composition. So next, the transformation process for the alloy involves a number of steps. When the molten alloy's temperature drops below its liquidus temperature, first solidification begins. The first stage is currently taking shape. The primary phase is a solid solution with a high copper, then often solidifies first. The form could resemble dendrite or coarse grain structure. And next, as the temperature falls, a eutectic transition occurs in the alloy remaining liquid. This suggests that it transforms into a copper-rich solid solution as a primary phase and a copper aluminium containing intermetallic complex as the eutectic phase of the two-phase eutectic mixture. The eutectic phase develops at a specific eutectic composition, which is the composition at which the liquid instantaneously transforms into a mixture of a solid phase. And next, last, after a liquid phase has completely solidified, the eutectic lamellar structure, the primary phase, merges to create a composite structure as a hypoeutectic transformation process proceed. Okay, now let's move on the microstructure and the cooling curve at this selected percentage weightage. So at T1, as the temperature is high, the present microstructure is only liquid or molten copper aluminium alloy. When it goes down the temperature, alpha will start to present in this microstructure and it called primary alpha. When it goes further cooling, beta will appear as well as perlite in this condition, and this alpha and beta will grow from the grain boundary. Okay, as for the cooling curve, when the alloy started to cool down, the phase is called cooling phase, but when it reached a temperature of 634 degrees Celsius, primary alpha will start to form and grow until the temperature reach 548 degrees Celsius. At this temperature, the eutectic phase starts and at the same temperature as this is an isothermal reaction. When it further cools, alpha, beta, and perlite will remain in microstructure until it reaches room temperature. So now let's look at the hypereutectic reaction, which is I choose 40% weightage of copper. Okay, as usually, we will go through the transformation first. What this means by point number 1 is a hypoeutectic copper alloy undergoes transformation as it goes from a liquid to a solid state, causing changes to the alloy's microstructure. When the solid aluminium concentration exceeds the alloy eutectic composition, this result is a hypoeutectic alloy. When the hypoeutectic copper aluminium alloy cools down below the liquidus temperature, solidification begins. The primary phase that forms during the transition is the eutectic phase, which is made up of a combination of primary solid solution phase and the eutectic compound phase, copper aluminium. The alloy continues to cool and the eutectic phase form a leftover liquid. In the lamellar structure that make up the eutectic phase, the primary solid solution and the eutectic compound are layered alternately, and the distribution and development of eutectic lamella depends on the cooling rate of the alloy composition. So the last point is, after a liquid phase has fully solidified, the hypereutectic transformation process proceeds, merging the main phase with the eutectic lamellar structure to create a composite structure. Okay, so let's move on the microstructure and cooling curve. So this is the microstructure of hypereutectic. So there is a slight difference from the previous microstructure because the previous microstructure is explaining about hypoeutectic, but this microstructure represents hypereutectic reaction. The only difference in this microstructure is the alpha and beta are switching place between them as the percentage weightage. of copper is 40 for hypereutectic. So, okay, the cooling curve also looks like the same as the previous cooling curve, but this time the beta formation took place at 577 degrees Celsius. The eutectic phase formation and N will be the same as hypoeutectic as they are happen at isothermal reaction. Okay, now I am going to explain about the composition and amount of phases at one temperature. At temperature 500 degrees Celsius, there would be two composition occur from 0 to 50% weightage of copper. So the first one is 1.5%. There is a single phase, which is alpha phase at the specific combination of temperature and composition. It is expected that a significant proportion of the alloy would predominantly exist in the alpha phase, indicating the majority of the microstructure would be characterized by the presence of this particular phase. And number two, I take 30% of copper. So there is two phase, which is alpha and beta phase. Given the particular temperature and composition condition, it is anticipated that the predominant fraction of the alloy would primarily reside in both alpha and beta phase, thereby signifying that the majority of the microstructure would manifest and coexist of this distinct phase in this region. The alloy's composition and thermal environment foster the formation and stability of both the alpha and beta phase, resulting in a pronounced presence of this phase within the overall microstructure composition of the alloy.
I'm Muhammad Hafizuddin. The next slide is the method of improving material properties. There are four methods that will be present in this slide, which is code working, solid solution, precipitation, and grain refinement. For the code working, basically code working is the reduction in thickness of the material or the specimen. In this process of code working, there is two procedures which is commonly used, which is code rolling and roving. Code rolling produces the plate and sheet for different values of thickness, while roving is the process of making the wire and tubes for different diameters and wall thickness. The purpose of code working is to increase the strength of the metal itself. The strength can be increased due to the number of dislocation increase compared to the original metal state. Dislocation also can be explained as the defects in the arrangement of atoms within a metal. Hence, the strength of metal can be increased depending on the number of dislocation that can occur by using code working. Next is the solid solution. A solid solution is a process where there is a mixture between alloying atoms and aluminum atoms. The effect of the mixture of alloying atoms and aluminum atoms increase the strength of the metal. The amount and type of the alloying element is the important factor to improve the strengthening of the material. For example, magnesium and manganese are the elements which can be added to the aluminum for the strengthening purpose. Thus, the strength of the material can be improved by undergoing the process of solid solution. Besides, this is the precipitation that can be defined as the process of conversion of a solution into a solid phase by converting the substance into an insoluble form. During the precipitation process, there is a small particles that form inside the metal which is called precipitate, where we can know this is the barrier for the precipitation, and it consists of an aluminum compound and alloying elements. Precipitates can be formed by the heating process continuously. The precipitation process undergoes the aging process which form the precipitates. The advantage of this process is that it can increase the yield strength of aluminium 3 times better than unalloyed aluminium. The strength of the material depends on the specific alloy and the temperature during the aging heat treatment. The precipitation hardening also can increase the conductivity of the material. Therefore, the precipitation is a good method to improve the strength as well as conductivity. Last but not least is the grain refinement, where the process of grain size reduction during the solidification process of metal casting. The barrier for grain refinement is the grain boundary. This process is the best to increase the strength due to the number of interfaces increasing between two grains. As the grain decreases, the grain boundary density will increase, which will avoid the movement of the dislocations and cause hardening to occur. The grain boundary will provide the crystal misorientation. From this, the dislocation will stop at the grain boundary and pile up at the grain boundary. Thus, the small grains will decrease the dislocation pile up, as well as increase the strength of the material. This is the engineering application of copper aluminum alloy. The copper aluminum alloy is mainly used in the aircraft construction. In the current industry company, we can see more aircraft construction and automotive engines use the aluminum copper for their engines and so on. the production of electronic and microelectronic components. As we can see, the aluminum copper alloy is the material where the conductivity is good, so it can be the electronic and microelectronic component for the certain industry that use. Next is the heat exchanger, aluminum beverage cans, and the marine applications.
So for the conclusion, in conclusion, the phase diagram of the copper aluminum alloy provide valuable insight into the microstructural evolution and the phase transformation within the system. The diagram shows the area of composition temperature where single phase and two phase region can be found. It shows the presence of various stages such as alpha and beta as their individual body. Engineering and material scientists can discover the ideal processing parameter to produce desired microstructure and customize material attribute by examining this figure. The phase diagram also makes it easier to comprehend how solidification behaves, how phase is separated, and how intermediate phase occur during cooling or heating process. The phase diagram also guide researchers in understanding phase stability and the effect of alloying element. It helps identify region of solid solution, eutectic reaction, and intermediate phase, providing a basis for alloy modification and the development of new material with enhanced property. The design and development of copper aluminum alloy with improved mechanical, electrical, and thermal characteristics for numerous industrial applications are ultimately made possible by this understanding. So in a nutshell, the copper aluminum alloy phase diagram is an effective tool for comprehending and modifying its microstructure. Researchers may create and construct copper aluminum alloy with specialized property for a variety of applications such as aerospace, automotive, and electrical sector by making use of this expertise. So precise control over material property is crucial for achieving the best performance. That's all from me. Thank you.